Ever wondered what challenges are faced while designing solutions for business problems using machine learning? Well, it's a fascinating journey filled with hurdles at every corner, from data gathering to cleaning, from transformation to interpretation. The process is quite complex, but one challenge stands tall among the rest: the dreaded prediction errors. You see, machine learning algorithms are like detectives. They aim to uncover the underlying patterns hidden in the dataset. They're on a mission to predict the future, based on what they've learned from the past. You could have the most meticulously engineered features, the most carefully selected variables, and yet these algorithms might still give you mispredictions. It's a bit like baking a cake with the perfect recipe and still having it come out a bit too dry or too moist. So even after thorough feature engineering and selection, why are there still huge mispredictions? To answer that, we delve into the concept of bias and variance trade-off. When we speak of algorithmic error, we're typically referring to three components: bias, variance, and irreducible error. Bias refers to the simplifying assumptions made by the model to make the target function easier to learn. It's like trying to fit a round peg in a square hole. The discrepancy is your bias. Variance, on the other hand, measures how much the estimate of the target function will change if different training data is used. If a model has high variance, it means it's highly sensitive to changes in the training data. It's like a chameleon changing its colors with the environment, except in this case, the environment is your training data. Lastly, we have the irreducible error. This is an error inherent to the algorithm that cannot be reduced regardless of our efforts. It's a bit like background noise, always there, and something we need to accept and work around. The goal of any supervised machine learning algorithm is to best estimate the mapping function for the output variable given input data. The mapping function is essentially the best fit line that represents the hidden pattern in the data. Now, different machine learning algorithms exhibit different levels of bias and variance. For instance, linear algorithms like linear regression, logistic regression, and LDA have high bias but low variance. They learn faster but may not perform as well on test data. On the other hand, algorithms like decision tree, KNN, SVM exhibit low bias but high variance. They're more flexible, but their performance can vary greatly with different test data. In essence, bias is an error of training data, and variance is an error of test data. The ultimate challenge is finding the right balance between the two, which is the crux of the bias-variance trade-off. But how can we determine the bias and variance of a model? Here's a way. Let's say your model's training error is 20%, and your test error is 19%. In this situation, your model exhibits high variance and high bias, making it an underfitted model. Now consider another scenario: a 2% training error and a 20% test error. Here, your model has low bias but high variance, indicating overfitting. The optimal model should have low training and test error, known as generalization error. So, how can we achieve this optimal model with low bias and variance? Well, we can reduce model bias and variance through hyperparameter tuning. Take random forest, for instance. It's a collection of multiple decision trees working in parallel. Each tree has low bias and high variance, but when combined, they offer a model with low bias and low variance. Boosting algorithms work similarly, using weak learners with high bias to collectively reduce variance. And that is how we can navigate the bias and variance trade-off in machine learning.